Welcome, this is Dean Waldo from PLU. This screencast will be a description of how to take iodine spectra, UV-Vis spectra from a physical chemistry lab, and fit it using what's called a multivariate fit to get 5 parameters at once. The other typical way the ground and excited state parameters are typically fit is to use a Birch-Spooner plot. Which works very reasonably, except you're always working with a portion of the data. So what we're going to do is take all the data, fit it at once, all the data meaning the data from multiple different ground states to multiple different excited states in the electronic level, and fit that. So thanks to a student, Greg Peters, for data from his lab analysis. So I'll use his data as an example here. In this table you can see the notation V_P stands for V prime. This data set is all starting at the ground state, the ground vibrational state 0, and going to various levels of excited state vibrational levels. And again, that's ground electronic to an excited electronic level. The next column is the wavelength in units of nanometers taken from the data acquired in the lab. And then that wavelength is converted to wave number. And so that's in units of inverse centimeter. All the data described here will be in units of inverse centimeter. The next table has all of the data from the ground state V double prime of 1 going to V prime of various levels. Again, wavelength and wave number. And last, the V double prime equals 2 data going to various levels of V prime in the excited state, wavelength and wave number. So what we're going to do is put this into a matrix. And that's a two-dimensional, multi-dimensional XY table, shall we say. So if you think maybe Excel styled, or if you've had linear algebra, a basic matrix. So let's make a new wave. In this case, I will call the new wave delta nu, just meaning it's the change in the variable nu going from the ground electronic state of some vibrational level to an excited state of some vibrational level. Instead of the normal definition of x versus y, we're going to have essentially z versus an x and y. So I'm going to say dimensions will be 2, and the number of rows needs to encompass the largest V prime value you're going to have. So I'm just going to pick a round number like 50. Since I'm going to put the rows representing the excited state vibrational level, and the columns will represent the ground state vibrational level. So I know I'm going to have only 3 columns here. So I'll choose 3 columns. That'll be for 0, 1, and 2 of V double prime. And then I'll have a variety of options for V prime. So I will say do it. Now I will open that new table I just made, delta nu. And notice what we have. The rows go from 0 to 49. And the excuse me. And the columns go from 0 to 2. So imagine those are going to be the coordinates for the various transitions we're going to have. We're then going to paste in the wave number information. So let's start doing that. So I'm going to pull up the V double prime 0 to V prime values. So notice they go from 13 to 39. Your start and stop positions may be different depending upon how far you've assigned. So I'm going to select that 17,225 wave number all the way to the 19,256.7, noting that it's 13 to 39. So I'm going to scroll up until I get to 13, and then I'm going to select all the way through 39. Then I'm going to paste right over that. Oops, and then I did not do that right. Go back, and I'm going to try it again. Copy, and I'm going to select all the way through 39, paste, and there we go. So note that we're going from V double prime of 0 to V prime of 13 through 39. So what we have to do is continue with the ground V double prime state 1 and 2. So let's go ahead and do that. Here is the data for V double prime of 1. I'll copy that. And note that it's going from 13 to 29. So I'm going to select 13, hold the shift key down until I get to 29, select all those and paste. And last but not least, I'm going to copy and paste the V double prime 2 data, again starting at 13, but this time only going to 20. So there's 13 going to 20, and I'm using the row number as my indice. Okay, so now we have a matrix. And let's go ahead and just take a look at this in a plot, and the way we can do that is a new type of plot, and that's going to be under the Windows menu, and I apparently didn't select the menu, so if you go down to New under the Windows menu, go to Image Plot, and if I slide this over here, basically I'm going to leave everything the way it is. For the Z wave, I'm going to pick that matrix I just made, Delta New, and I'm going to say do it. And what you get is sort of an image. Now notice the black area. Those are the areas we didn't have wave number information, so they're showing up as zeros. That's not very useful because that's not going to help us in our fit. So what we have to do is go back to the matrix, and we have to tell Igor that wherever there's a 0, there's really not a number. And the way you can do that in Igor is to enter the acronym NaN, which stands for, wait for it, not a number. That's sort of a joke. Okay. So not a number. So notice when you enter that, it shows up with nothing. So you can copy that and just keep pasting wherever there's a 0. And notice in the image in the background, that black color is going away. We could take and select to 3 rows, but we'd have to make sure we paste always to 3 rows just to speed up things a little bit. And then I can just do this one manually. Go back and look at the image. We see our data here. Remember, this is on the left axis V double prime, the bottom axis is V prime. We still have to do the other black area, so let's go down here. So not a number. Oops, again. And I'm just going to start doing the 2, and then I'm just going to select always the same number that I had copied. And I'm going to copy 4 this time. I'm going to do 4. And 4, and then I'll just do NaN here and NaN. Since I don't have any data in this set, I'm just going to select those, and I'm going to hit, on a Mac it's Command X or a PC Control X just to delete those data points. Now if we go back, we can see more resolution. So the colors you see represent the magnitude of the wave number in that matrix. Okay, coffee break. I'm back. Let's go ahead and make this plot a little bit more professional, I guess. Let's select all the axes, and on the axis tab we're going to turn on mirroring, turn off the standoff. We're not going to put minor tacks because our axis system are integers. I like to have the ticks on the inside. For the axis label, on the left side I'm going to call that V prime, parenthesis, oops, no, this is V double prime. V double prime, ground state. And I'll fix that parenthesis. Then on the bottom axis, that'll be V prime, parenthesis, excited state. And let's say, do it. You can't see that. It's, there we go, it's off the screen. Now it's on the screen. notice that we have nicer axis systems now. I'm going to get rid of the 0 to 10 quantum number on the V prime where we don't have data, and I'm going to give a little buffer around it so we can see it easier. So I'm going to double click on the axis, and on the axis range, let's move this into the screen you can see. I'm going to say 10 to 45, so give it a little buffer on the left. I'm going to say -1 to 3. And note that it's giving a rectangle as the intensity and filling that in, even though really we just have a single point at the integers, like 13, 14, etc. for V prime and 0, 1, 2 for V double prime. I'm not a fan of the grayscale, so if you double click, or two finger click I should say, on the back, on the background, oops, two finger click somewhere on the data, that's what I mean, and if you go down to modify image, we can actually change the color scale. So I'm a fan, whoops, not of that one. You won't be able to see it, but it's violet, orange, yellow. Now you can see it, violet, orange, yellow. And if I say do it, you can see now that the color sort of scales nicely from a low value to a high value. So we're ready essentially now to do a fit. And what we're going to do is fit both the V prime and the V double prime data at once. So we'll have 5 parameters coming from equation 2 in Garland et al. So I'm going to open up the analysis curve fitting window. Let's put this in the window you can see. And click on the function and tab data. I've made the function already, I called it transition wave number. And let's just hit edit fit function so you can see what that looks like. Okay, so we have 5 fit functions, VE. So in the book these all have the tilde over it, meaning they're all in units of wave numbers. So that is the distance between the bottom of the 2 potential energy surfaces. And then VE1, or that stands for prime, so VE prime and XE prime, those stand for the harmonic and anharmonic contributions to the excited state. VE double prime and VE and XE double prime stand for the same things but for the ground state. Those are our fit parameters. The independent variables would be V1, which will stand for our V prime, and V2, which will stand for our V double prime. Pay attention to the order. So in this case, V1 is the first variable in the function, V2 is the second. And if we go back and look at our matrix, I guess we can't do that right now, but when we go back and look at the matrix, we'll see that the rows show up first, which are the V prime or V1, and the columns are second as V2 or V double prime. And you can go ahead and pause the video and look at this equation. You'll see that it is equation 3 from Garland, etc. So I'm going to test compile. It's compiled successfully. I'll say replace the function now. That would be exactly like what you would have done with new fit function. So then I'm going to select the wave, and the only wave you should see here would be the matrix that you made. So I'm going to select delta nu. If I unselect from target, you can see I have a bunch of other things here, but what you want is the matrix you made. If you have that graph up on the top level, you will then see only the delta nu if you have from target checked. Leave x and y as calculated, and it'll use the indices from that matrix as the variables of the function. We have to do a couple other things before we actually do the fit. We don't have to do anything in the data options side, but we do have to in the coefficients. Since this is not a normal function, it doesn't know how to sort of guess as to the initial values. So I would suggest using something like 16,000 wave numbers for the VE. For the VE prime, I'd use about 120, let's just say 120. and something like 0.006 for the XE prime, maybe 200 for the VE double prime, and about 0.006 again for the VE or the XE double prime. One thing I noticed when working with this is that sometimes, probably given due to data, we only have 3 values in the ground state, so forcing the XE terms to be greater than 0 is important. And when you open up yours, you'll probably see this selected as none for constraints. So you'll see one value or one column for initial guesses. So what you need to do is go to constraints and do from constraint or coefficients list, and then put 0 in the lower constraint for both XE fitting parameters, so for the XE1 and XE2. At this point you can check output options, but just maybe set destination auto and residual as auto trace, and say do it. And what you will see is this window will tell you the fit progress. It took 4 iterations to get this fit. Note that the V parameters like 132 and 212, 13 or so, and the values for the XEs are given there. If we say OK, it shows the fit parameters in the window. Also notice that there are these lines it's added. It's difficult to show a fit function to a 2-dimensional fit, so what they do is they show contour lines of the fit function. Notice at the highest energy levels you're seeing about 19,200 wave numbers going down to 17,000 wave numbers. But these collection of 5 parameters are your fit values. You'll also get another graph, and it'll be res underscore whatever your name is for that matrix. And if you again go down to modify image, you can switch the colors to something you like. I like this one, but you can see that this set of colors is much flatter, so this is the difference between the fit of that 2-dimensional function and your actual data. Should be pretty flat, and just shows you the noise in that data. I'll move it off to the side. Anyway, so now you have your fit variables. All of these should be in units of wave number, and these are exactly what you can start comparing with the values from the reference book we used in lab. Anyway, that gets you hopefully to being able to do what's called a multivariate fit, and in this case we're multivariate fitting the function for the change in wave number from a ground vibrational state in one electronic level to an excited electronic level at a different vibrational level. Thank you.